The world industry is shifting its gas compressor drivers from steam and gas turbines to electric motors. This is because an electric motor drive system has been proven to be superior and has many more advantages in comparison with turbines. While aeroderivative gas turbines have some improvements over conventional single-shaft gas turbines, the electric motor drive system still excels in many aspects. System efficiency, availability, maintainability, operability, controllability, as well as environmental load. Plant owners are always looking for means to reduce their operating expenses and environmental emissions to achieve better efficiency and operability, as well as the best energy balance in their plants. In this respect, turbine drivers might be a headache for them. One of the best solutions for this issue would be conversion from turbine drivers to an electric motor drive system. That is why some owners have already replaced their existing turbine drivers with electric motors, and they are happy with the result. Here are some of the advantages of electric motor drivers. Higher efficiency than turbine drivers. Less CO2 gas emission. Less maintenance time and cost, and easier operation and better operability. Electric motors do not emit CO2 gas. PDS, therefore, can reduce the CO2 gas emissions of a plant and make it greener. Conventionally, a speed-up gear is necessary to drive a compressor by an electric motor. Especially when replacing a steam turbine with a motor, additional space is required for the gear, which means expansion of the existing compressor train area. Our high-speed motors do not require the additional gear, and you can now enjoy the motor driver solution without expansion of your train space. Here are some comparisons between our high-speed motors and regular 4-pole motors. While a high-speed motor itself costs more than a regular 4-pole motor, a relevant drive and isolation transformer cost the same, as the motor output is the same. As you can see on this table, high-speed motors have a number of advantages due to the gearless configuration. To start with, costs related to the gear unit and its operation are non-existent. Total efficiency is better as there's no gear loss. You need less lube oil, a smaller oil cooling system, less oil piping, a smaller footprint of skid, and fewer monitoring instruments. Alignment is easier thanks to single coupling. System reliability is higher and less maintenance is required as you do not have to worry about the gear. In order to make PDS more stable and reliable, we provide technical solutions. The power grid may not be stable, and sometimes instantaneous voltage dips may occur. Ride-through control or automatic restart function is provided as standard functionality to minimize the decrease in compressor speed. Restart is available for power recovery within 2 seconds as your project requires. As for the compressor drive, motor torque ripples can cause fatal torsional vibration. In order to avoid this issue, PWM control based on a fixed pulse pattern is applied for the TM Drive XL series drives as a standard feature. Sideband waves are not generated because PWM pattern periodicity is kept and symmetrical. The torque ripples are just n times the output frequency. There are no low-frequency harmonics. If the pattern is selected to reduce the harmonics, the magnitude of the harmonics is lower than that of synchronous PWM. The TM Drive XL series boasts a long MTBF of more than 20 years. We have supplied almost 100 high-speed electric motors for replacement projects and new projects as well. Let us now introduce some examples of our successful projects. The first example is a steam turbine replacement project in Japan. 3 steam turbines were replaced with 3 1,840 kilowatt induction motors. The motor speed was 12,000 rotations per minute. This CO2 gas emission reduction was brought about by less boiler fuel used in the refinery. So, the change to an electric motor was instrumental in reduction in both crude oil consumption and CO2 gas emission. The second example is a gas turbine replacement project in Japan. Another Japanese company successfully reduced greenhouse gas emissions and also freed itself from the trouble of obtaining obsolete gas turbine spare parts and poor technical support to maintain the turbine. The motor rating was 8,400 kilowatts and 5,773 rotations per minute. According to the customer's evaluation, maintenance cost was reduced by as much as 94%. MTBF of the turbine driver system was 4 years, while that of the electric motor driver system is 15 years. Another gas turbine replacement was for a refinery plant in Japan. The customer intended to maximize their plant efficiency to save energy. The driver was a 2,600 kilowatt induction motor with a speed of 9,470 rotations per minute. The next example is a new gas pipeline project. The Russian user did not want to use lube oil due to a very low ambient temperature. For this reason, their solution was neither a gear reducer nor oil-lubricated bearings. They chose an induction motor, 4 megawatt, 8,000 rotations per minute, with magnetic bearings. Another example is a new project for a booster compressor for a natural gas plant. The project concept is a utility-free solution. So, the choice was an air-cooled motor with magnetic bearings, an induction motor rated 3,300 kilowatt output, 8,959 rotations per minute. TMEIC has successful experiences with motor and drive systems for gas pipeline booster compressors. One example is the West-East Gas Pipeline project in China, where TMEIC has supplied high-speed synchronous motors, 31 sets of 18 megawatt, 5,200 rotations per minute, and 12 sets of 18.5 megawatt, 4,800 rotations per minute. Now we can see an apparent technical trend of compressor drivers from gas turbines to LCI, or load commutated inverter, and from LCI to VSI, or voltage source inverter. In order to mitigate motor vibration risks, TMEIC takes 3 basic measures. The first one is to support stator assembly with springs. This photo shows a 2-pole motor stator assembly supported with springs. This can reduce vibration level by 50%. The second measure is a high-speed rotor balancing machine. We can perform balance tests up to 8,000 rotations per minute. The motor of the balance machine is also a high-speed motor, and its rating is 3,000 kilowatt, 8,200 rotations per minute. The third measure is the vibration analysis by computer-aided design, or CAD, of stators and rotors to minimize their vibration levels. Another important technical aspect is harmonics. TMEIC calculates harmonics to confirm that our PDS will comply with the harmonics regulations, such as IEEE 519 and GBT 14549 without harmonics filters. We simulate air gap torque generated in motors by VSI drives and provide the data to compressor suppliers. This enables them to perform more reliable torsional vibration analysis of their compressor trains. TMEIC has delivered more than 1,000 units of 10 MVA class VSIs. We are capable of providing comprehensive engineering for high-speed power drive systems. If you are interested in replacing your existing turbine drivers with high-speed electric motors, or if you are considering high-speed electric motors for your new projects, TMEIC is the one you should count on.